To say that the space sector is booming is almost an understatement. In 2020, global space-related activities generated an astonishing $447,000 million American dollars, with commercial activities accounting for almost an 80% of that. This phenomenal growth is due to a series of factors that have converged in the last decade and retrofit each other. In particular, as far as satellites is concerned, we have first, the huge capacity and flexibility of the latest telecom satellites, high throughput, flexible, software-defined satellites with inter-satellite links. Then, the craze of the so-called new space, the democratization of space, characterized from space systems becoming smaller, lighter, cheaper, and easier to operate, that have opened the doors to new players, including new countries such as New Zealand, India, and also new companies, both small, lots of them, and large, such as SpaceX or Blue Origin, and also new satellite formats, such as MiniSats, that are not especially new, but that thanks to payload and other components miniaturization, cheap launches, and the possibility to cooperate among them in constellations are now flourishing. And last but not least, what is being referred to recently as the new ground, that takes elements from Industry 4.0 to fully unlock the potential offered by the new space as driven by three key technology enablers: virtualization, goal-driven orchestration, and artificial intelligence. Focusing ourselves in telecom, all these factors have enabled a new paradigm beyond the traditional model of small fleets of big geosatellites to that of large, say more than 100, constellations of small or even very small LEO satellites. Some actors such as OneWeb or SpaceX are well in their way to deploy their large constellations, with others such as Amazon or Telesat starting to do so. This new concept introduces, however, new challenges, not only in the space vehicles, but also in the ground segment. The solutions historically in place for ground control software or GEO satellites are no longer applicable to LEO large constellations. For starters, the satellites are far simple in terms of needs of the control software, so traditional control systems are too large and too complex with too many features to properly fit these small satellites. On the other hand, the key driver here is scalability. Both the ground antennas and the control software need to be able to seamlessly scale to hundreds or even thousands of satellites as the constellation grows, while at the same time ensuring the cost effectiveness as a major driver for producing feasible solutions. Let my colleague Hugo tell us what we are doing in GMB for coping with this situation.
In 2018, we took the decision of launching a completely new, different and disruptive initiative, with the goal of creating a new GMB product in charge of monitoring and control large constellation of small and nano satellites. The idea behind was not to execute a classical project in the form of a predefined number of milestones with a closed scope. Instead, we defined a framework taking into account the need of a deep investigation on our customer needs, and also a high level of freedom of the team to incorporate innovative solutions. Then we started what we call MiniSats initiative, which has two main different objectives. On one side, the first objective was to develop a completely brand new ground software. The current existing product at GMB for monitoring and control ground stations and satellites provide a huge range of functionality. This is exceptional for classical GEO satellite fleets or even for constellation of medium-sized satellites. But we consider that this approach was not fitting the new paradigm required for large constellation of small and nano satellites. A completely different alternative based in a simpler approach and focused in a high scalable and cost-effective solution was identified as necessary for this case. We also saw the need of providing APIs to permit keeping the interaction with not only our existing GMB product, but also with other external solutions. The second objective was aimed to align GMB portfolio of ground software solutions with modern technologies. The current extraordinary evolution of the software, especially boosted by Internet and the web in general, made us to understand the benefit of the usage of already built components and modern architectures, which are commonly used today in software, and being able to incorporate them into our system. Then, for the execution of the project, we selected a group of experimented engineers coming from different areas of the Satellite Control and Mission Planning Business Unit at GMB. The goal was to work with personnel with demonstrable experience not only in developing ground software, but also with high operational background. We decided to work following an agile framework, Scrum in particular. Then, in the form of iterations, the development team had been building the system by incorporating regularly new functionalities defined by our product owner. The product owner is also supported by other engineers with remarkable software development and operational knowledge. These other engineers come not only from our team of stakeholders at GMB, they are also other external users such as our own customers. This was made possible thanks to the regular presentation of the system to relevant actors at different moments of the development process. In that sense, we were able to retrieve their feedback and reorient our development to the most appropriate solution for our customer needs. At the end, we are producing an event-driven architecture built in the form of microservices with relevant new technologies such as Grafana in the front-end case or InfluxDB for the data storage layer, and with the ability to be deployed in everywhere, at the customer premises or remotely, for instance, in Amazon Web Services, thanks to the usage of containerization. And now, my colleague Mario will present in detail how our new MiniSats system works.
Hello everyone, I'm Mario Alvarez, one of the developers of the MiniSats system that we can see in the video wall behind me. The MiniSats system is based on different components, on a microservices architecture based on several APIs, and the main interface we have is Grafana. That is what we can see here. The main advantage of using Grafana, a part of its power, is how configurable it is. We can configure it for every different client, so it can be adapted to every need they have. Now what we are going to present is a demo of the main dashboards we have as an orientation of how we can use the system, what information is available to the user, and how it can be accessed. This is the main dashboard we have, the entry point of MiniSats. It's a dashboard where we can see the position of every satellite we have, the passes ongoing, the next passes we have, how many satellites are visible inside, the bandwidth. I have spoken of the whole fleet, but one of the main ideas behind MiniSats is to be able to filter. We can filter by fleet, we can filter by label. At the end, that is, for example, the activity passes, there are static labels, dynamic labels, that allow us to filter the information so we can see only what we need at any point. Here we have configured two fleets with the public information about them of several OneWeb satellites and several Starlink satellites, just as a demo. So we are not processing the real telemetry, of course, but we are using their orbital positions to simulate the passes on several antennas. The blue points on the map are the antennas, the green points are the satellites on pass, the orange, the satellites which are not on any pass at the moment. From here we can access any satellite and see more details about that particular satellite. That is what we are going to do now. This is the satellite view for a particular satellite. We can select which one we see here. We will see the fleet it belongs with its icon, how is the telemetry, and several items we have configured, like batteries, payload temperature, some flags. We can see also some graphics like voltages and temperatures also, the passes we have in the time span configure, and also that we have not seen it before, plans and activities. A plan is what is configured for each satellite to run on board, one or several procedures, and the activities are the procedures themselves. Here we can see that we have run several activities at the different passes that have been occurring in the last minutes. And those passes have resulted in the sending of several commands that we can see here. So we have all the information for a satellite aggregated in a single view. That is this one. We could change the time span or use all the Grafana standard information to navigate it and see it not only for the current moment, but from the moment in the past. One of the main advantages of using this system is that we can aggregate information for lots of satellites and see it at the same time. For example, here we can see the passes of all the satellites at the same time to see when each satellite has gone through any station. The same visualization is also used for the activities. We can use the activities and see all the satellites, which activities and when they have been executed at the same time. As I said before, it's not only good to see all of them, but to be able to filter and see the ones for a particular fleet, the ones that are currently on pass with the dynamic level, or if we only want a single satellite, we could even use this visualization for it. The same is also possible in this view, as both are equivalent. One of the advantages of using Grafana and how it can be configured is that we can expand a dashboard like the single satellite dashboard we have seen before to, for example, a two satellites dashboard where we can compare the telemetry of two different satellites at the same time. See their flags, their referring values for same telemetries or different ones as the client needs are, and compare the telemetry, the voltages of both of them seen at the same time or the temperatures. Also, we can switch the offset of the time, so we can see one satellite in the present and the other in the past, or even the same satellite in the present or in the past at the same time, so to compare different maneuvers. One of the core points of a microservices architecture is not only to see the payload, but to also be able to monitor and control how everything is going in the system. How we can do it? Also with Grafana. With Grafana, Prometheus, and Docker, we can monitor everything that is happening at CPU level, network, disk, memory, the number of containers running at any point. This allows us to have a single point of access, both from the user and the user who monitors the system and control how, if more hardware is needed or how everything is going, and everything is integrated in the same place. So at the end, these are the main dashboards we have in Grafana. There are other entry points from the application to be able to configure the activities we have seen or to be able to define or remove satellites. But this also can be done through the APIs we have defined, so the system can be easily integrated with other tools from the client or other GMB solutions to be able to expand their functionalities. And this is it. Hope you have liked it, and any questions are welcome. Thanks you all.